So topic 1.5 is atomic structure and electron configuration. This is a nice little diagram showing some of the orbital shapes, the 2p's, the 3s, the 1s. And remember, the s's are spherical, the p's are dumbbell. We're going to go through all of that in this particular section of notes. Let's look at our learning targets for today. The enduring understanding atoms and molecules can be identified by their electron distribution and energy. Now, electron configuration is 1.5. We will not get to like the speed of light equals the wavelength times the frequency, or the energy is equal to Planck's constant times the frequency. We won't get to these calculations and things until Unit 3. They have them separated into two totally different topics. So note that we will get back to this, the energy part, the energy part of the distribution later. But today you should be able to write an electron configuration of an element or ion using the Aufbau Principle. Write valence electron configurations and determine the number of unpaired electrons in an electron configuration. So we'll be touching on how to read those as well. Before we get on to writing electron configurations, we need to revisit the idea of the quantum model and where it came from. So Schrodinger, he did his wave equation, wave functions equation, and which, pretty much started the whole idea of quantum mechanics. And his wave equation, really, you don't have to calculate it by any means. It is represented by the psi, the Greek letter psi here. It's just showing the statistical likelihood of where the electron is 90% of the time. And from that, also the data gathered shows the electron densities and the different shapes of these orbitals, these three-dimensional spaces. Now remember, the electrons, they behave as particles and waves. And you could go back to the previous slide and watch that video. It's about 10 minutes long to kind of go through the development all the way up to where they came up with the quantum mechanical model based off of not only Schrodinger, but Schrodinger. You have Heisenberg, you have other scientists that contributed, Planck, Einstein. It was kind of a build up, and then came out the wave function equation, the wave equation that helped determine the electron density. The electron densities and solving these wave functions gave the shapes of the orbitals, and now you could track the shapes of the orbitals for where the electrons are going to be located. Now this is a probability too. Don't forget that we're talking about probabilities here. 90% of the time they fall within that space. So the wave functions to quantum numbers, solving the wave function gives sets of a set of orbitals, which are those three-dimensional spaces based off of the wave function graphs and their corresponding energies. Each orbital describes a spatial distribution of the electron density. And each orbital is described by 3 quantum numbers. Now, we're not going to go fully into quantum numbers and reviewing that, although the first quantum number is n, which is the principal energy level. That corresponds to the periods on the periodic table, the rows. Then you had L. L is I think the angular momentum number. This one's just telling you the shape of the orbital, whether it's S, P, D, or F. And then you have M sub L, which tells you the orbital within the sublevel or subshell. So say we had a P orbital, there's 3 in the P. Remember, like this one would be -1, 0, and 1. You don't have to know quantum numbers for the AP exam. I did attach notes and example problems at the end here that are optional if you want to go back and revisit quantum numbers. I would suggest that you do, because quantum numbers, you will see them in college if you're going to take a college level chemistry class, as well as the fact that they are on the SAT2. So if you're planning on taking the SAT2, the SAT2 curriculum and knowledge is not the exact same as the AP exam curriculum. They do coincide pretty well, but there are some things that are not on the AP exam that are on the SAT2, and quantum numbers is one of them. So keep that in mind if you're planning on doing the SAT2 this year. And I do recommend it if you are going to take it, that you take it, a couple weeks after the AP exam when the chemistry is still fresh. So the orbitals, here's a nice graphic of all the orbitals in their sublevels. So S is our sphere shape. The P's are those dumbbell shapes. There's 3 of them. There's the one on the X plane, the Y plane, and the Z plane. The D's, they get a little bit more creative in their shapes, with look more like balloon animals. And of course, the F's are more complex. Now you can watch this little video here that kind of shows you how the orbitals for scandium stack on each other. It's a nice little 3-minute segment or so, but it kind of gives you the perspective of how they stack with relationship to the nucleus. I threw in this graphic as well to help with realizing not only here's your principal quantum numbers, so like row 1 on the periodic table, the subshell or sublevel designation is 1s. That means there's 1 orbital. The s's only have 1 orbital, the one in that particular energy level, and the one closest to the nucleus only has the 1 sublevel and the 1 orbital. So it's a 1s. That's in the first energy level. The second energy level has a 2s and a 2p. So you have 2 sublevels. You have a total of 8 orbitals. There's 2 in the s and 6 in the p. And so basically you can, I'm sorry, not 6, 3. There's 1 orbital in the s, 3 in the p. That's a total of 8 electrons, because you can put 2 electrons in each orbital. That's where we're getting this 4 over here, 4 orbitals for the second sublevel. I mean, for the second energy level, The third energy level, you have a S, P, and D. So now we have 1 orbital for the S, 3 orbitals for the P, and then 5 orbitals for the D. That's where we get this total of 9 orbitals in that particular energy level. This would be the 3rd row on the periodic table. And then starting in the 4th one, now we have all 4 sublevels. So 1, 3, 5, and 7, and that's where that 16 comes from. Total of 16 orbitals in principal energy level 4, 5, and down the table. These are the M sub L numbers. Like I said, you don't have to know them, but this is where those are, like 1, 2, 3 orbitals for the P, 1, 2, 3, 4, 5 orbitals for the D, and so forth. The Aufbau diagram also shows where the energy is for each level and each orbital. So we have our subshell or sublevel here, 1s, for the principal energy level 1. There is the only 1 orbital there in that energy level. The 2s, though, or the energy level 2 has the 2s and the 2p, but the 2s is slightly lower in energy than the 2p. And you have your 3 orbitals located in the 2p. And as you can see, you go up there, the energy. This is where it gets a little out of order. You fill the 4s, which is just slightly lower than the 3d. So the 3d is a little bit higher energy than the 4s, just slightly. But they're going to fill following the Aufbau principle, where it fills the lowest energy level possible before moving on to the next orbital. You're not going to need to memorize this diagram because we're going to use the periodic table to fill these orbitals and not have to memorize it this way. This is too complicated to remember. Defining the Aufbau principle, atomic orbitals, they need to fill the lowest available energy levels before occupying higher ones. And that was part of the learning target, so make sure that you are be able to do this. So it's the 1s subshell, 2 electrons, and then the 2s subshell, then 4 electrons would go in the 2p subshell. So we would fill this one, and then 4 would go here into the 2p for oxygen. Now, why it fills that way, if you remember on the periodic table, oxygen has 8 protons. So that means a neutral atom of oxygen is going to have 8 electrons. So you would fill 8 electrons. Now the notation for the electron configuration, remember, you have the 1 for this is the principal energy level. This is the shape of the orbital, and then the superscript tells you the number of electrons. So this is going to be the number of electrons in that particular orbital. So the 2s2 means there's 2 electrons filling the 2s orbital. In the 2p4, that means there's 4 electrons filling the 2p sublevel, which has three orbitals in it. You can use the blanks or you can use the boxes. And we'll be talking about Hund's rule next, but just to show you, remember Hund's rule where you put 1 in each orbital first before you pair them up. So it'd be 1, 2, 3, and then 4. So the only one that would be paired up would be the first one. So this is where that unpaired part of the learning target is coming in. You have to be able to determine how many of them are unpaired in a configuration. So speaking of Hund's rule here, looking to unpair the electrons unless you have to pair them up. Remember, electrons are negatively charged. They repel each other anyways, so they would rather be more spaced out if they could be. So this is the example for nitrogen. I can tell it's nitrogen because it has 1, 2, 3, 4, 5, 6, 7 electrons. And nitrogen is 7 on the periodic table, which means it has 7 protons. The correct way to fill it would be to put 1 up arrow in each of the 2p orbitals. The incorrect way would be to pair up the first one and so forth. Here is the example of how to apply Hund's rule. Now we call the 2p or the d's or the f's degenerate orbitals because every orbital in there is of the same energy. So like the 2px, the 2py, and the 2pz all have the same amount of energy. So they're called degenerate orbitals. Now, Pauli exclusion, going over the opposite spins, and only 2 electrons in the orbital. So if we're looking back at the oxygen example, 1s2, 2s2, 2p4, and filling that 2p4, 1, 2, 3, and then this one pairs up. They're going to spin in opposite directions. And I know we do an arrow up and an arrow down, but it's really clockwise and counterclockwise. So the up arrow is indicating clockwise spin, the down arrow is indicating counterclockwise spin. Only 2 electrons can fill one particular orbital. That's following Pauli exclusion principle. And by doing so, this is where the spin, if you remember m sub s of the quantum numbers, that was the plus a half or minus 1/2. So the clockwise spin, the counterclockwise spin, that allows no 2 electrons to have the same exact 4 quantum numbers because the last one would definitely change up. One would be spinning clockwise, the other one would be spinning counterclockwise. So plus a half, minus a half. Once again, don't have to know this part, but that's where Pauli exclusion comes into play. This is the main point though, opposite spins and only 2 electrons per orbital. This particular summary video I put in here as well if you'd like to go back. For some people, it's been a long time since you've done electron configurations. However, I would tell you to start around 6 minutes on this video. The first 6 minutes is all about the energies and the more about the energies rather than the placing them in their configurations and orbital diagrams. So if you're going to do, watch this video, I would start around 6 minutes. We'll come back and watch the beginning part when we get to Unit 3, where the energy stuff for the electrons is more of a factor. So filling in the orbital diagram for oxygen, going to go ahead and do that. Remember oxygen's number 8, so 8 electrons. You would put 1 in the 1s, and then you'd fill this one completely following Aufbau Principle. So now I'm down to 6 electrons. I would fill this one completely, 2 before moving on, putting them opposite spin due to Pauli exclusion principle. Now I have 4 electrons, once again, following Hund's rule here at this point, 1 in each box, and then this one gets paired up. So I would say there are 2 unpaired electrons in this configuration for oxygen, and you could write the configuration based off of the orbital diagram. There's 2 electrons in the 1s, 2 electrons in the 2s. Oops, not supposed to be 6 there though. There should be 4. I think I was getting ahead of myself there. Oops, not that either. Okay, 2p4. So this would be the configuration. This would be the orbital diagram. The boxes and arrows are the orbital diagram. The configuration is the 1s2, 2s2, 2p4. Now, this is the important part, the periodic table. Instead of memorizing the Aufbau diagram, we're going to use the periodic table. There's a few things that are out of order on the periodic table, so I'm going to point them out to you. 1s is hydrogen, the other 1s is helium over here. The other 1s is helium. Helium technically has 2 valence electrons, so they could have organized it where they put helium in the group 2 based on valence electrons. However, helium is an inert gas that's not reactive, so it belongs more with the noble gases. You're going to follow, so the tall column over here, this is the S block. The tall columns to the right are the P block. The transition metals in the middle are the D block, and then the inner transition metals, the lanthanide and actinides, are the F block. And they insert right here. So remember, the periodic table is super long. So you just follow the table though, and you keep adding up your electrons as you go. 1s, and then you go through the 2s, here's the 2p, 3s, and then you go over here to the 3p, 4s. This is where it gets out of whack again. The 4s fills lower energy, it's slightly lower than the 3d, so you fill the 4s. This one is one row behind. The 3d comes after the 4s. So this is like n-1 in terms of this number 3. So 4s fills 3d, then 4p. 5s will fill after the 4p. 4d comes after the 5s, 5p, and so forth. If you get down here to the 6s, it goes 6s, then you have to go down here to the 4f, then come back up to the 5d and go over here to the 6p. But we're probably not going to do any ones that are that long in terms of the periodic table. They'll stick more in this range over here, the 4Ds, 4p kind of range in terms of writing out electron configurations. That's the generalized one. Here I also inputted this periodic table in your notes because this also identifies the column. So everything in this column fills to the 1s1. So that's 1 electron in the s. Anything in this column will fill to the 2s, or s2, 2 electrons in the s. This is the d1. This over here would be the d10. This is the p1, all the way over here to neon, which is p6. So you can see the n here is just goes with the row. So if I'm talking about argon, it's going to be 3p6. But if I'm talking about xenon, that's 1, 2, 3, 4, 5. This is a 5p6. They all have p6 though, 6 electrons filling that particular sublevel completely. Don't forget, once again, 6s right here, it goes down here to the f's. And the f's and end on YB and NO, LU and LR are actually the starting of the D block. But remember, that's inserts to the periodic table. It makes it really super wide. And like I said, I don't think we're going to be doing much in the F block down here. Writing the ground state electron configuration for antimony. First thing I would do is get out my periodic table. And I would locate antimony here. Here is antimony. Looking here, then I just start at the top of my table and I start filling in the electrons. This is the S block, first row, this is the 1s. So 1s2, it fills completely. I just keep working all the way down here till I get to antimony. Lithium and beryllium represent the 2s, that's 1 electron, 2 electrons, so 2s2 fills. Boron, carbon, nitrogen, oxygen, fluorine, and neon. This is the 2p row. And that's, if we get all the way through it, we're filling all 6 electrons, so this would be 2p6. 1, 2 here, 3s fills. Here goes the 3p, we're filling that completely. And now this is the 4s. So K and Ca, potassium and calcium, they represent the 4s. We're filling through the 4s. and scandium all the way down here to zinc. That is the entire 3D. Don't forget, this is the 3D row. So now 3D10 fills. This is now the 4p row. So we're going to fill the 4p's completely. 4p6. Almost there, all the way down here to 5s. 5s2 fills. This is, since the row above was 3D, this is now the 4D row, filling that completely. 4D10. And last but not least, we're ending on antimony. So 1, 2, 3 into the 5p. So our last part of the configuration would be 5p3. Yes, this one's a long one. That's why they don't make you do these ones down here. They take too long. So that's how you would completely fill out the ground state configuration for antimony. And yes, it ends over here on 5p3. Use the periodic table, start at the top. You'll get faster and better at it as you practice. Let's talk about electron configurations of ions. First of all, we have to deal with our cations, and it's cation is how you pronounce that, atoms that have lost electrons. So that means they're positively charged. They have, pluses on them. And in order to write out a configuration for a cation, you must remove electrons from the outermost energy level. So let's look at an example of the nickel 3 ion. Nickel 3 here. What I do is when I'm looking at these, I look at where nickel lands on the periodic table. And if you look at your periodic table, it's in the 3D row. It's 8 into the 3D row. It's like 2 to the left of zinc there. So I'm looking here. This is regular nickel. Now, if I lose 3 electrons, so I'm going to take away 3 electrons. The thing I have to know, though, is I have to remove them from the outermost energy level. So the outermost energy level here is actually the 4. So the 2 and the 4s have to go first. So I'm going to remove them from that 4s first. Outermost energy level goes first. Then, so I will take away 2 of the electrons from this one. That means I have to take 1 electron away from my 3D8 because that's now the next most outermost energy level. And that results in the ion configuration for nickel 3 here. So remove them from the outermost energy levels first. And know that, yes, the 4s or the 5s will be higher than the 3D or the 4D. The other looking at here is the anion example. Anions are atoms that have gained electrons. These are the negatively charged ones. And you add electrons, let's change that to 2 here, to the outermost energy level. You just add. So for arsenide here, arsenide is our ion here. It's gained 3 electrons, arsenide. I write out the configuration for arsenic. And if you look on the periodic table, arsenic's over there under nitrogen column, I believe, and it goes to 4p3. So this would be the long, huge configuration for arsenic. Just regular arsenic, not the anion arsenide. But I need to add 3 electrons in here because I have a -3, so 3 electrons. If I look here, I'm going to be adding to this 4p first. How many electrons can the p hold? Rule 6. So guess what? If I just add 3 to it, I've maxed out the 4p. Good to go. And it ends up being 4p6. Now, this ion, of course, is isoelectronic with, in the 4p, that one's going to be neon, then argon. This one's krypton, right? So it's going to be isoelectronic with krypton. And remember, this is why the elements form ions is to have a more stable configuration, and the noble gases have the stable configuration, and so they try to mimic those the best they can. Now the transition metals are a little bit different. They have a little bit more options since they have those D ones to work with. But this one, arsenide, is going to be mimicking krypton, same configuration as krypton. All right, one more slide and then we'll be done for today. Valence electrons. The electrons, the outermost principal energy level. Just wanted to show you the example here. Neon is 2s2, 2p6, similar to the krypton, which was 4p6. So it has 8 valence electrons. So you can see the ones in the same group have the same number of valence electrons. And basically all you have to do to figure those out is add the S's and P's, because those are the outermost energy levels, to figure out the valence electron number. Because we're going to be doing valence configuration, so we need to know what valence electrons are. So if we're looking at selenium here, I'm just going to take my 4s, which is outer, my 4p, and add these two together. That gives me 6 valence electrons. And if you look at the other ones in the group, oxygen, sulfur, they also have 6 valence electrons. Oxygen, though, remember, was 2s2, 2p4, but still the 2 and the 4 add together to give you 6 valence electrons. And as you can see, I highlighted them in red for you. And yes, you would take the 2 electrons that are in the 4s plus the 4 electrons in the 4p to get your total of 6 valence electrons. Now, if you look at this group, it's oxygen, then sulfur, then selenium, and then I think it's tellurium. But if you look at that group, this is group 16 on the periodic table. And we all know that group 16 has 6 valence electrons. But the difference is that oxygen is going to be 2s2, 2p4, sulfur would be 3s2, 3p4, and so forth. It's just a difference of an energy level row as to why they're a little different. Yes, the S and P are the two sections. Those are going to be the ones that are the outermost for the row, and they're going to be the ones that you would add up to get your valence electrons. And how you're going to write valence configurations is based off of the S and P in the outermost energy level. So, exercise 2. Pull up your periodic table. First, write out the electron configuration for zinc. Based off of your configuration in A, you should be able to determine the valence electrons. And then I want you to go ahead and, based off of that information, figure out what the configuration would be for zinc 2+, where it has formed its cation. So I'm going to go ahead and give you a minute to do that. So looking at this periodic table, part A is to find the configuration for zinc, then determine the number of valence electrons, and then figure out what the configuration would look like if it formed the zinc 2+ ion. So on our periodic table, I've already outlined zinc here, found it on there. Just going to start at the top of the table and follow the patterns in order to write out my configuration. Then you start working from the top of the table down to write out your configuration. Hydrogen and helium represent the 1s block, 1s. Okay, so we're going to fill those 2 electrons in the 1s. We have to get down to 30 electrons, so because zinc has 30, we're going to keep going down the table. Lithium and beryllium, this is the 2s section, so we're going to fill that next. Following Aufbau's principle of filling the lowest energy level possible first. So 1s fills with 2, 2s fills with 2. Now the boron section, all the way through neon, this is your 2p row. This is the 2p row. And yes, we're going to continue all the way down to 30 electrons, so we're going to completely fill that with 6. Then sodium and magnesium represents 3s, completely fill that. Aluminum, silicon, phosphorus, sulfur, chlorine, and argon is the 3p. Filling that. Now, this is where it gets a little dicey. We have the 4s. The potassium and calcium is the 4s. We fill that completely. The D block, don't forget, the D block starts one row behind, so this is actually the 3D. And we're going all the way down to zinc. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to get to zinc. That means the 3D is completely filled with 10. And this is the ground state configuration for the regular zinc atom. The second part B was looking at the valence electrons. So what we're going to do here is examine our electron configuration and look for the valence electrons. What's the outermost energy level out of all of those in the configuration? 4, good. So we're looking here at the 4s. That is going to be our valence electrons. So if you look at the 4s, how many electrons is it holding? It's holding 2. So zinc atom is going to have 2 valence electrons. And a lot of these transition metals also have 2 valence electrons. There are a few exceptions because some of them don't exactly follow the Aufbau principle, but that is not on the AP exam, so we're not expected to cover it either. I did put examples of that at the end of the notes, though, if you're interested in knowing which ones do not follow the Aufbau principle, typically. The last part is looking at finding C, which is the zinc 2+ ion configuration. And what did we say about when it's forming a cation? What are you going to do with your electrons? Lose them. And where do we lose them from? The outermost. And in this case, yes, outermost happens to be the 4s, which I saw somebody put. That's great. 4s is the outermost energy level. So this is the one that's going to be lost when we're writing out the zinc 2+ ion. So you would write in everything else, just like before, 3p6, but the 4s now would be crossed out, and we're just going to go straight to the 3d10. And that would be our configuration for the zinc ion. And so if you want to recheck it, I put all the answers here in the slide for you where you can go back and take a look. But hopefully you kept up with us while we were working out the problem. Now for noble gas configurations. Noble gas configurations is an abbreviated way of doing electron configurations. They don't expect you to do noble gas configurations on the AP exam, however, I do believe they would accept those answers. The other thing is they're not going to typically give you really long configuration elements because of the nature of the AP exam where it's timed. So keep that in mind when you're writing out your configurations. It's probably easier to just go with the regular configuration unless it's a super long one. The first rule, of course, is you need to find the noble gas in the row above and put the symbol in brackets. You start in the row of the element and add the rest of the configuration. So for instance, if we're looking at cadmium on the periodic table. All right, I also like this periodic table. It's not the one you get for the AP exam, but look, you can like highlight and it shows you all the metalloids. There's all the, what do they say, the post-transition metals, the lanthanoids or lanthanides, alkali metals, noble gases. You click on the element themselves, it pulls up all of this data over here about the element. So this is a fun periodic table. We're looking at cadmium though, which is right here. It's number 48 on the periodic table. And if I'm following the rule for the abbreviated noble gas configuration, you would want to go up one row and over to the right. So krypton is going to be its noble gas that represents cadmium. So you would write the krypton in brackets first. Then you're going to come back here and start in the row that cadmium's in, which is row 5, or principal energy level 5. You would add in the 5s. The rubidium, strontium is the 5s. Yttrium all the way through cadmium would be the 4d. And you would just tack that on to the end. And that's how it would look. Based on what you just saw of me doing that, you could write out the entire configuration, but that might take too long in terms of time. Sometimes it's easier. You would end up looking, the reason why the noble gas works here is basically it's taking the spot of this long part of the electron configuration. Everything from 1s2 to 4p6 is the exact same as krypton. And then you just say everything's the same as krypton to this point, and then we add on the end to get to cadmium. And it is better for the longer, the ones that have more electrons. This is a much better, more efficient way of writing the configuration. Now, what I would like you to do for exercise 3, I'll give you a couple minutes, write the expected ground state configurations for sulfur, barium, and selenide. You can use the noble gas configurations if you'd like, but realize these ion ones, they're a little bit more tricky when it comes to those noble gas configurations, since they end up having the same configuration as a noble gas. You might want to make sure that you write them out with the longhand. So go ahead, take a moment, give you like 2 minutes, go ahead and practice. So let's look at these ones right here. Sulfur, barium, and selenide. Let's look at sulfur. Once again, starting at the top of the table, going through the 1s, filling that completely, filling the 2s completely, filling the 2p completely, filling the 3s, and then to get over here to sulfur, you have to go 1, 2, 3, 4 into the 3p. So 3p4, very good. This would be for sulfur. Now, if you wanted to do the noble gas configuration, you could go up here over to neon and use neon in brackets, like so, and then you would just start in this row with the one that sulfur's in and add the rest on. So this would be the 3s2, and then 1, 2, 3, 4, 3p4. This is how you would write the noble gas configuration for sulfur. Let's go ahead and look at the barium ion. Different color though, let's make it nice and pretty. All right, let's do purple for barium. Barium's over here in the alkaline earth metals, and it's also a 2+ charge. So it has lost 2 electrons. If I go back to electrons, 1, 2, now I'm at xenon. So barium 2+ has the same electron configuration as xenon. That means it's isoelectronic. Oops, let me spell correctly. Isoelectronic with xenon. They have the same electron configuration. Iso meaning same, electronic representing the electronic configuration. And remember, the idea of why barium's going to lose 2 electrons to begin with is for stability purposes. The noble gases are always stable on their own and inert. They're unreactive because they don't need help from other elements in order to become stable. Barium, however, forms a +2 ion in order to achieve the noble gas configuration as the same as neon. And that's why we're going to say they're isoelectronic. Now, I could write out the entire configuration for xenon, which takes a while, or I can go one up from xenon and use krypton as my noble gas here and put krypton in the brackets, and then just start in this row with xenon and finish off the rest. So this would be 5s2. Remember, this is 4d through cadmium is 4d10. And then in indium all the way to xenon, that is going to be 5p6. And that's how you would write out for the barium 2+. If you wanted to do the full length one, you can. You don't have to. Easier to do it with the noble gas configuration. Yes, that's exactly how you would do the noble gas configuration for xenon or barium 2+, which happen to be the same configurations. As stated before, you cannot just put xenon in brackets. That's not going to work. That's not a noble gas configuration. Selenide. So here, let me change colors one more time so we have a different color on the periodic table. Go for the dark red. All right, so selenium's right here, but if selenium gains 2 electrons, really, which one do we look like? Selenide has the same configuration as krypton. Very good. So it's isoelectronic with krypton. And selenide is achieving the stability by mimicking the krypton configuration. So what I can do here is I can write out the configuration for krypton, which isn't as long, or I can use the noble gas configuration for krypton, which would put me at starting with argon in brackets, like so. And then I would start here in this row, and this would be 4s2, 3d10, and then I get all the way over here to krypton, which is 4p6. You're welcome to write out the full configuration and add on the 1s2, the 2s2, 2p6, 3s2, 3p6, and that would be, this is all the same as argon. So either or would suffice as an answer for finding these electron configurations. And as you can see here, these are also written in here if you need to go back and check the answers for exercise 3. Valence configurations. You have to be able to do those as well. Writing out the configurations for phosphorus and lead is more time consuming. So I would recommend, instead of doing that, look at your periodic table. We look at our periodic table and we're looking for valence configurations. We want the S's and the P's in the outermost. That's where we're looking for. So those two examples, one was phosphorus on that slide, the other one was lead. Now writing out the configuration for lead is quite lengthy, and I don't want to do that. So let's start with phosphorus, which isn't as lengthy though. So if I'm writing out the the valence electron configuration for phosphorus, I really just need to look at the outermost energy level. It's in row 3, so N equals 3. That's going to be the outermost energy level for phosphorus. And it's going to have 2 in the 3s and 1, 2, 3 in the 3p. That's all I have to do to figure out the valence configuration. I don't need to write out the full configuration. I just need to look for the outermost. The other thing, once again, how we said, you know, that this was 1, this is 2, this is 3, 4, 5, 6, 7, and 8 for the valence configurations. Helium has 2, it's an exception. But why were we able to assign this group to having 5 valence electrons? Well, that's because they always have 2 in their S and 3 in their P. And that's where that general rule came from. Looking at lead, let's change colors for lead. Okay, which is down here. Once again, I need to look at the outermost energy level. And the outermost energy level is based off of the row, so N equals 6 here. So I know that leads, we got to count up the S's and the P's for lead in order to get its valence electron configuration. So there's 2 in the S, so 6s2, because that's which row I'm in. And then I go 2 into the 6p, 6p2. Valence electrons, though, 2 plus 2 gives me 4. Guess what that matches? Our general rule of this column, all the elements in this column have 4. Well, let's think about this. Why would that be? Like carbon's configuration would be 2s2, 2p2. It's just a different row, but it's 2 and 2. So it's also going to have 4. Silicon's the same way, except for silicon would be 3s2, 3p2. So that's where that idea of numbering the columns for the valence electrons came from. And here you can once again go back and check the answers. I highlighted them here. You don't need to do this big long configuration, or even the noble gas configuration is kind of a pain for lead because you have to go into the F's. So I would just look at the row that's the outermost energy level and do the S and P's. Makes it go a whole lot faster. Exercise 4, a different interpretation of how a problem can be phrased. They give you the configuration in the problem and just say, tell me what's the valence configuration. This should be pretty simple because you don't have to write it out. All you have to do is look for what? The S and P for the outermost. So in sulfur here, what's the outermost one, S and P? The 3s, yeah, so you look here at the 3s. There is your valence configuration. 3s2, 3p4. Now this is barium, regular barium, not barium ion. It's a little bit longer, but which one do we need to find? Which one is the outermost S and P, or S and P? All the way here at the end, and they typically are at the end, but you might have some D's in breaking them up. But 6s is the outermost energy level here. So it is just simply 6s2, which also coincides with the fact that barium is an alkaline earth metal in group 2 and only has 2 valence electrons. So that's where that 2 comes from, because they are all s2s in that group. Now the solenoid, which happens to be the ion form, what's its outermost energy level and how many electrons would be in there? Yes, we're looking at the 4s and the 4p, and in this particular case, mimicking, I think the solenoid was what? Mimicking krypton. So it would be 4s to 4p6. And that is correct, a total of 8, mimicking that noble gaseous configuration. Very good. And once again, you need to go back. They're written here for you, so you can go back over those answers. This one's totally a fun one, a totally different approach. You have been given atoms in their ground state, so they are not excited. They are in their ground state configurations. Which atom contains exactly 3 unpaired electrons? And I'm talking unpaired here. What do I need to really examine in order to figure this out? Whose rule has to do with pairing? Hund's rule, good. Somebody said Hund's rule, correct. Hund's rule, and when we want to do Hund's rule, what do we really need to use? What representation? Yes, those boxes and arrows, we call those orbital diagrams. We need to use orbital diagrams. And then we can tell who's paired and who's unpaired. But the periodic table is also very helpful. Let's look at the periodic table. And it said we have A was calcium, B was tin, C was cobalt, and D was, what was D? Bromine? Bromine. All right. Now that I have my list of things to examine, I'm going to look at my periodic table. And the pairing and unpairing, is that going to be at the beginning, the middle, or the end of the configuration? It's definitely at the end. So I only need to look at the end. I don't need to look at anything else. Don't need to waste my time. So here's calcium. Looking at the end of calcium. What's the end of calcium? Which orbital? 4s. Good. So if I'm looking at calcium, here's my 4s orbital, and I have 2 electrons in it. Up, down. Anything unpaired there? No. So guess what? Calcium does not win this question. Let's look at tin now. Here's tin over here. Outermost energy level for tin. Which one is it? 5p. Good. So we have the 5p here. And there's 3 orbitals in a p, so I need to put 3 lines out. How many electrons in that 5p? 2. 1, 2. 1 up arrow following Hund's rule, the second up arrow. How many unpaired electrons do I have? Only 2, so not 3. So tin is now out of the game. Let's keep going. Let's take a look at cobalt. Cobalt here. There's cobalt. What is the last orbitals for cobalt? 3d. How many orbitals are in a 3d? 5. So we need 3d here. So 1, 2, 3, 4, 5, 6, 7. Following Hund's rule, put 1 in each first, then pair them up. Are there 3 unpaired here? Yes, cobalt happens to be the winner, but let's just check bromine for fun. Just for fun. Always like to do it just to verify. Here's bromine over here. What's its outermost orbital going to be? Sublevel. This is the 4p. So if we're looking at bromine, which happens to have a 4p, how many electrons is in the 4p for bromine? 5. Good. So we do 1, 2, 3, 4, 5. Only 1 unpaired there. So definitely cobalt is the one that wins. All right. So cobalt was the winner. On to Coulombic attractions now. Second part of topic 5. Totally different approach here. You're going to qualitatively apply Coulomb's law. You're comparing the magnitudes of the attractive force between the nucleus and electrons in different subshells of an atom or sublevels. And you're going to be looking at them from the same sublevels in atoms and ions, but they're different atoms and ions. The other thing that you're going to have to do with Coulomb's law is qualitatively apply the amount of energy needed to remove an electron, which is known as the ionization energy. Now, ionization energy is also a periodic trend, which we're going to revisit when we get to 1.7. They strategically place it here for their various reasons, but it usually you know of ionization energy in the trend category. The first thing we want to do is review what ionization energy is so we know what we're talking about when we have to apply it. Ionization energy is the energy required to remove an electron from a gaseous ion or atom. This is the generic equation for ionization energy where you have your neutral atom. It's breaking apart into the cation and to the electron. So for example, down here with this magnesium example, what you should notice here, this is the ground state neutral atom of magnesium. The first ionization, which is over here, is measured in kilojoules per mole, because that is a measure of energy, kilojoules. Breaks apart into Mg plus and 1 electron. It's a fairly low ionization energy. Now, what we should know about magnesium is that magnesium is an alkaline earth metal. It's in group 2, so that means it has 2 valence electrons. I'm just going to note that right now. So for the second ionization energy, where you have Mg plus, breaking off the second electron to form Mg2 plus, that is 1445 kilojoules per mole. So far, not a huge jump here. Now, if we take that Mg2 plus ion and want to remove a third electron, which is the third ionization energy, it would form Mg3 plus and then the electron. But what you should notice here is that ionization energy jumps to a tremendously high amount. Why is that? Because when you get to that third electron, you're now ripping electrons away from the core section, not the valence. The valence ones are more easy to lose because they're not held on as tightly by the nucleus. The core ones, though, are bound more tightly. There's a stronger force of attraction, so it's a lot harder to remove them. And you're creating, when you create Mg2 plus, you're creating the noble gas configuration. But you're not going to get that noble gas configuration with Mg3 plus. It's making it very unstable. So in order to do that, you have to use a lot of energy to create that situation. Yes, ionization energy does decrease as you go down a group, and we're going to talk about why that is right now, actually. Coulomb's law. Coulomb's law, this version is the physics version. This is where you would plug in numbers and calculate and get your force of attraction, and you'd use your constant and all that stuff. We're not calculating this. They said qualitatively apply it. We're using this version down here, where the force of the Coulombic attraction is proportional to the magnitude of the charges, which is Q1 and Q2, over the distance, which is r squared. Keep in mind, though, when you have charges of the same sign, like positive, positive, they repel. So this Coulombic force would be positive, repelling the same thing because negative times negative gives you a positive. But if they have opposite charges, you're going to get a negative force where it releases energy in order to establish that attraction. But we're applying this here, and we have to really look at it in terms of the numerator and denominator and how it affects certain situations. We won't be doing this version at all. No plugging and chugging of numbers at all. We're just going to look here. If we change the magnitude of charge, how does that affect our force? If we change the distance, how does that affect the force? So my first model here, distance versus the attractive force. So looking here, we all have one proton per group, one positive charge per group. You see the shorter distance here, it has the higher force of attraction. The greater the distance, the force of attraction gets very small in terms of the distance here. So basically, as we see, the greater the distance, the force of the attraction on the electron is going to decrease. Now, this force of attraction is coming from the nucleus because the nucleus holds those protons, which are the positive charges. Distances, when we're talking about distance type example problems, they're really referring to comparing elements in a group. So this is why going down a group, the ionization energy would decrease. Because if you see here, this is group 1. We have lithium, sodium, potassium, group 1 alkali metals. The lithium nucleus, there's only one energy level between this valence electron and the nucleus. And the distance obviously is much shorter. This valence electron, we have 1 and then 2 energy levels in between. Distance is greater. Looking at potassium, 1, 2, 3 energy levels in between. All right. So therefore, we're going to have a greater distance and the attraction for that electron is going to decrease. There is another factor in here that's also decreasing the strength, and it's the shielding effect caused by these core electrons in the other energy levels. So there is a little bit of that happening too. But when you're phrasing these questions, they really want you to talk about the distance. You can refer to the shielding as well, but if you miss the distance part of the explanation, they will not give you the point because they want you to go back and refer to Coulomb's law. So if we're looking at Coulomb's law, where it's the Q1, Q2 over R squared here, the denominator, the distance increases, that's going to reduce that force. And that means the amount of energy needed to overcome the force is lower. And that's what we're talking about. Ionization energy is the amount needed to remove the electron. Well, in order to remove the electron, you have to overcome the attractive force between the nucleus and the electron. So that's what we're talking about here. You need to refer to the Coulomb's law to explain the answer. The distance is longer, so therefore the force of attraction is lower, and the ionization energy would be lower in that case. The other part of the equation is the magnitude of the charges. So if we're looking at Q1 and Q2, which is the numerator this time, this part, that's what we're referring to when we're talking about the magnitude of charges. And looking here at our examples, the A has 1 proton, D has 2 protons, the E has 3 protons, the 4 has, F has 4 protons. The distances are all equal here. So we're not even looking at that part of the equation. Distances are all equal. But as you change the magnitude of charges, so this is +1, this is 2+, this is 3+, this is 4+, okay? Magnitude of charge much greater down here. Look at this force of attraction. It's higher. So when you add more protons, more nuclear charge, the greater the force of the attraction on the electron. That's also going to make the ionization energy higher. It's going to be harder to remove the electron. So when we were looking at distance, we were looking at the ones going down the group. When we're looking at magnitude of charges, we're looking at ones that are in the same period, in the same row on the periodic table. Like sodium, aluminum, and chlorine are all in period 3. period 3 on the periodic table. They all have 1, 2, 3 energy levels. So the energy level amount is not going to affect this problem. So now we're looking at the magnitude of charge, the Q1, Q2, proportional to the F. We're looking at this part. What we can compare about these, because they all have the same energy level, so the shielding and that effect, the distance are all going to be pretty much the same. Sodium has 11 protons. It's number 11 on the periodic table. Aluminum has 13. It's number 13 on the periodic table. And chlorine has 17. It's number 17 on the periodic table. So which one has a higher magnitude of charge? That's going to be your chlorine. 17 protons. That's 4 more protons than aluminum. So that's why this force of attraction on the valence electron over here is much higher, and it has the bigger arrow. Adding more protons, the greater force of attraction are on the electron. And that's how you're comparing the ones in the same period. So nuclear charge, more protons, greater force, higher ionization energy. Now let's apply this to an exercise. This exercise, though, isn't comparing groups at all. This one is just comparing electrons in different subshells. Does a 1s electron have a higher or lower ionization energy than a 3s electron in a magnesium atom? So looking here, locate your different electrons so you have a good reference point. Tells you here the S's. So 1s, these are your 1s's. These are your 3s's. Magnesium only has 12 protons, and it's going to have 12 protons affecting all the electrons regardless. So it's the same magnitude of charge. So looking at Coulomb's law, we're not worried about this part because that part's not changing. That's 12 protons, 1 electron. What we need to concern ourselves with is the distance. Does the 1s have a higher or lower one based off of its distance? Higher, good. So, and then when you answer a free response question like this, the first thing you need to do before you explain is make your claim. So, does it have a higher or lower ionization energy? You need to write higher ionization energy. Declare it. Make your claim. Then you go into your explanation. Now, we would want to, you want the full point on this free response question, you need to reference your Coulomb's law. You need to write it in there. All right, so let me show you how this should look for a full point on this free response question. You state your claim, higher ionization energy. According to Coulomb's law, write it in there. The R, or distance, of the 1s electron is closer, or you could use the word shorter, to the nucleus and will have a stronger attractive force. Thus, it takes more energy to remove the 1s electron. They want to see this very thorough explanation showing that you understand that the part of Coulomb's law being affected here is the one on the bottom. Yes, you would want to include the formula to reference it. Anytime you're referencing a formula in your explanation, you should include it. You can't just say by Coulomb's law and not state the formula. Always state the formula. Good question. But in order to get the full point on the AP exam, and they love to ask Coulomb's law questions, I'm just telling you, you would need to make sure that this is how you would explain it. And you'd say the distance is closer or shorter, has a stronger force of attraction, thus the energy needed to remove it is much higher. That's why I'm declaring higher ionization energy. Another question, let's take a look. This is a fun one. Which of the following ground state electron configurations represents the atom with the highest first ionization energy? This is a multiple choice question though, and you don't have to explain it. You just have to figure it out. Any ideas of what I should do here? Electron configurations. The first ionization energy is the energy needed to remove the first electron. What should I do with these configurations first? How am I going to compare them? What should I do? Find their elements. I like that idea. That's a great idea. Let's find them. It said 3p3. I saw a 3p4 sulfur. What were the other ones? It was 4s1 and 4s2, right? So here we go. 4s1, 4s2. These are the elements that we're dealing with. Phosphorus, sulfur, potassium, and calcium. And you can see they group them very close together. So it's not that hard to evaluate quickly, especially for a multiple choice question. You know, this one has 19 protons, calcium has 20 protons, phosphorus has 15, sulfur has 16. These are all the reference points that we need for Coulomb's law. First thing I would do when I see this is decide on looking at Coulomb's law. Keep writing it down. But as you can see, potassium and calcium I'm going to cross off immediately because they're in principal energy level 4. That means this distance factor is going to be so great that it's going to make the force go down. And they have no way of competing because they have that extra energy level with phosphorus and sulfur in terms of ionization energy. So I would cross them off mentally off my list. And then I would compare phosphorus and sulfur. And then I need to look at the magnitude of charge, the top part, the magnitude of charge. Which one has a higher magnitude of charge? Sulfur, yes, they're in the same row, so they have the same number of energy levels. Distance isn't a factor. The higher nuclear charge, more protons. So that's why potassium and calcium, because of that 4th energy level, they're not within contention. Phosphorus and sulfur have the less distance. They have the 3rd energy level, but sulfur has more nuclear charge because it has one more proton. So that is why I would select B from that particular choice, and that would be the correct answer. Sulfur would be the highest. Yes, go ahead.
What has a greater effect on the ionization energy? Is it like going down the group? Does that make it like significantly lower energy than going left in a row? Does that make sense? Like which one has a greater effect?
If you remember the trend of ionization energy, it increases as you go up and to the right. Going down a group really knocks down that force. You're adding shielding and distance. Following the ionization energy trend, you would know that too. Like these two have lower than anything in the 3rd energy level. They're going to have lower ionization energies. This is where this set of notes ends. And we're going to go ahead and shift over to the PES. If you'd like to look at quantum numbers, they're here. But that's for your optional, knowledge if you want to pursue that.